Number systems. To understand how bits and bytes are stored and translated into information humans can read, we must learn about numbers and various number systems that you may or may not be familiar with. Numbers were used before there was formal writing. A number is a value representing a particular quantity in order to count, make calculations, or show order. It can be expressed in words, symbols, or figures. Even people in primitive times used numbers. This counting stick, found in Lubombo, Swaziland, was made more than 35,000 years ago. The cuts in the bone record the value known today as 29. Numbers are represented by numerals. A numeral is a name given to a number so that it can be identified. The cuts on the Lubombo bone were an ancient form of numeral. The two terms tend to be used interchangeably, which is why they're so commonly mistaken to be the same. But there's one major difference. A number is the same regardless of the numeral used to describe it. A numeral can be different while still describing the same number. If asked how many tires a car has, the answer can be given by handing someone the marbles below. The quantity of marbles represents the number of tires and is a true answer. Regardless of the numeral used to describe it, the number is the same. Today, that answer can be represented in many different ways. For example, do any of the following numerals look familiar? All of them would be a true answer and represent the same number. We have 4 as a decimal number, we have 4 in Roman numerals, and 4 tally marks. The numeral 4 is part of what is called the base 10 numeral system, or the decimal system. It is the most common and accepted way of representing numbers. The numeral IV is part of the Roman numeral system. It is a system that uses letters to represent numbers. A number system is an organized group of symbols that represent numbers of a given set in a consistent manner. New number systems have been created over time, but do not replace each other, unlike languages, which evolve and change. For example, Old English writings would hardly be recognizable to the current English texts. Number systems, however, once created, do not change, and therefore are understood across millennia. For example, the Roman numerals used in Roman times are exactly the same now, just less frequently used. Once a more efficient number system is available, it becomes the standard, but the old systems are still used. Most number systems actually have a purpose and place, even today. Roman numerals are still used to track Super Bowls. Hash marks are still used to tally and keep count in various ways. Beyond those two number systems are the base number systems. In mathematics, a base is the number of different digits or combination of digits and letters that a number system can use to represent numbers. In other words, a base 10 number system has 10 different digits and/or letters and must express every number using different combinations of those 10 characters. A base 2 number system has only 2 different characters to choose from in order to represent every number as well as other types of data. Base 10 is the number system used most, so much so that most people think it's the only one. It is the system most commonly mistaken to define numbers. As stated previously, the base determines the number of characters used in the system. So this system uses 10 characters, called digits, that look like this, 0 through 9. Recognize them? Why do you think base 10 has become the most preferred? With 10 fingers, it's only natural that we gravitate toward a base 10 number system. And though it's a reference we don't often think about, digit is a synonym for finger. The decimal number system is another name for this system. Any number could be used as the base for a number system. However, in this course, we will be using just 4 base number systems. These are the systems relevant to computer science, because while base 10 is most readable to humans, the other ones below are most readable to computers. We will be going over each one, how to convert between them, and how they relate to computers in later lessons. Let's start out by seeing how the decimal system works. We take it for granted, but understanding it will help us understand all base number systems. The base 10 number system is the one we are most familiar with. It contains the 10 single digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. By combining different combinations of these digits, we can create different numeric values. For example, the number 427 is not part of the 10 single digits that make up the decimal system. However, it does consist of a combination of 3 of the digits in the system, 4, 2, and 7. But 427 is not 4 plus 2 plus 7. Each digit represents a different number due to its place. The 10 in base 10 represents more than just how many digits the system has. It also represents the value each place will have. The base 10 indicates that each digit must be multiplied by 10 to a certain power in order to create numbers beyond the initial 10 digits. But what power? It starts on the right. The value of the rightmost digit is multiplied by the 10 raised to the power of 0, which is 1. Then each digit to the left of that is multiplied by the base 10 raised to 1 greater power. In this case, it creates places for ones, tens, hundreds, thousands, etc. The notation for numbers in base 10 is denoted by a capital DEC, short for decimal, subscript after the numeral, like here. Notice that individually, each digit is one of the 10 digits available in the base 10 number system. However, each digit's value is determined by its place in the numeral, as shown below. The 2 is worth 2, since it's 2 times 10 to the 0. 10 to the 0 is 1. The 6, however, is worth 60, since it's in the 10 spot. So 6 times 10 is 60. The 8 is worth 800. The 4 here is actually worth 4,000. And when you add all of those together, you get 4,862. The digits of the base 10 system are not unique to that system. They can be used in other systems and represent different values. For this reason, it is important to denote the numeral with its proper subscript when working with multiple number systems. The subscript notation of each is an abbreviation of their name, as shown below. Base 10 uses subscript BIN for binary. Base 8 uses subscript OCT for octal. Base 10, as we've said before, uses subscript DEC for decimal. Base 16 uses subscript HEX for hexadecimal.